pleasure to introduce our guest today, is Aleksandr Molochkov, and who will tell us about his recent and ongoing progress on lattice field theory as applications to non-uniform systems. So please, Sasha.
Yeah, hello everybody. So today I like to make some review on some of our recent work, which is somehow unified the problem of the simulating non-uniform systems on the lattice. Actually, lattice field theory provides as a powerful toolkit for numerical simulation in field theory, and this approach. Okay. This version of field theory has its pluses and minuses, and which is outlined here shortly. And so originally it was invented by Wilson according to his idea of universality, that we can cut our scale, our theory at certain scale, and all physics behind this scale does not affect on the larger scales. In this sense, it's some kind of way of regularization of the local field theory. And the big advantage of this is calculations beyond the perturbation theory. Even we can calculate in the different regimes, and weak coupling and strong coupling regimes. And we can use different field theory models. Even we can try to consider some non-local things. And some properties like kind of phase diagram of the theory, which is very difficult to calculate in the perturbation regime, and so on. Because of that, this lattice field theory is widely applied in the quantum chromodynamics and analysis of the quantum chromodynamics properties and so on. But there are some cons in the lattice field theory, which are very serious. And one of the points, which is somewhat, I put it in the pros and the pluses of the theory, and I will show in my talk why it's a good side of the lattice field theory, this imaginary Euclidean space-time provides us imaginary time approach in connection with thermal field theory, and it is very good for some kind of condensed matter applications, but also it's good for some fundamental questions, especially connected with non-uniform theories of the lattice, non-uniform systems of the lattice. And there are some real serious cons. First of all, some of the fundamental symmetries are absent. In fact, in the lattice itself, when we factorize small distances scales, we even do not have translation symmetries, but they are present in the continuous limit. But there is no, for example, continuous rotation symmetry even in the continuous limit. So it's always C4 symmetry of the lattice, so it's cube, so you can rotate it only on the P/2 angle, so you cannot rotate it on the smaller angles. And it is serious problem because we are working in Euclidean theory. That means that our Lorentz group somehow integrated in this Euclidean space-time, and the absence of the rotational symmetry means that we do not have Lorentz group here as well, and and it produces problems for the for using spinor field, and it's well-known problem in the lattice that we cannot treat fermions on the lattice in a somehow good way, so we have to do some estimations, making some, I would say, some artificial things to try to put fermions on the lattice. This is why actually I do not discuss in my talk at all these fermion degrees of freedom. So I will discuss only gauge fields, which nicely fit to the lattice field theory, and also some kind of scalar field applications in the end. You'll have time. And another problem, no time evolution. So we can study only averaged over time quantities. And it's difficult to understand some time evolution, some problems with which observables, which depends on the choice of the 3D hypersurface, and it's very important. First of all, an analysis of bound states, analysis of the analysis of the different kind of relativistic properties of the many particle systems and so on. But it's somehow it can be solved also by this. This is why I put it in the pluses. So using this thermodynamical kind of tricks in analyzing field theory on the lattice. So what are the non-uniform systems? So here I will discuss several examples. So first example, when we have boundaries in our field theory. Actually, from the fundamental formulation of field theory, all these boundaries, it's a serious problem because usually we treat our field theory, quantum field theory approach, as we have some in and out states at the infinity. We have some properties at the infinity, and then we can quantize our theory and analyze kind of only asymptotic states as a physical. Boundaries somewhere in between this in and out infinities, they break all this picture, and it's not clear how to treat it consistently in the field theory. But there are interesting effects. It's strange. It jumped somewhere. No, okay. It's so what it is kind of Casimir effect. So this is famous effect, and it's up to now there is no kind of clear understanding if it's vacuum effect or it's just forces between two neutral somehow bodies like van der Waals forces or so. There's a point of view of Schwinger, and there's another point of view of Bryce DeWitt and so on, who say that it's vacuum effect. So we will discuss it shortly in my examples, what Lattice says. And also some interesting non-abelian Casimir effect on boundary states. Another non-uniform systems, it's acceleration of the lattice, so rotation and acceleration, same. So we will consider there's two things. So from practical point of view, acceleration is important because usually when we even in particle physics, when we analyze quark-gluon plasma, when we analyze other interesting states, acceleration is very important because it can be, in some cases, accelerated state, but we treat it as a kind of fusion. Here, namely in these two cases, we will use the tricks from the thermal field theory and connection of the thermal field theory with so-called the Tolman-Ehrenfest effect or von Roux effect. So when we can treat our non-uniformity as a kind of temperature non-uniformity on the lattice inhomogeneity of the temperature. And other applications which I hope to touch, it's a rather unusual application of quantum field theory to modeling of proteins. This is also from point of view of non-uniformity, it's most non-homogeneous system, very complicated and so on. And from first point of view, it seems that it's okay. Homopolymer, it's possible to analyze, but protein, it's very difficult to imagine. I will try to show.
So to understand better, when you are saying about temperature, do you mean the connection with imaginary time? So time is changing. Non-uniform.
So temperature on the lattice, I will show it's not simply imaginary time, it's scale. It's scale of the imaginary time. So if you manipulate scale of the imaginary time, you change the temperature of the system. And then you can introduce some tricks actually related to all this Tolman effects and so on, how you can introduce non-homogeneous scale for the time direction on the lattice. So in fact, it's manipulations with scale. So, okay, so I will make short intro to the lattice field theory, not going much into details. So we make discretization of our space-time. So there's directions. It's Euclidean 4-dimensional space-time instead of the mu electromagnetic. Point our field theory. It's great invariant pocket. So we can manipulate properties of the plaquette. Then we making rotations, so making time going to pure imaginary time. Instead of the path integral, we get the statistical sum, which we can numerically calculate on our lattice. One of the important observables on the lattice, it's a Polyakov loop. So Polyakov loop, it's product of the time-oriented links and over the periodic conditions. So it makes a loop which is connected with free energy of a probe charge. So then free energy of the probe charge is a logarithm in the it's free energy of probe charge in the thermal equilibrium at the temperature defined by the imaginary time direction and its scale of this imaginary time direction. And this Polyakov loop is the order parameter of the theory, because if you have confinement, deconfinement, phase transition, then you have, so in the finite temperature, so it's 0 in one phase and non-zero in other phase. So we can use the Polyakov loop as an order parameter. Okay. Okay, so space-time with boundaries. First, it was proposed by Casimir, the idea that if you have two boundaries, so-called Casimir plates, where the gauge field equals 0, so electric field, so that means that it's perfectly conducting plates. Then its limits spectrum of vacuum fluctuations between the plates. And then there should be energy density between the plates and out of the plates are different. It leads to so-called Casimir forces. And it was proved at the experiment, and it was inconsistent with the idea of the infrared cut of the waves here, which was considered as a kind of proof of the existence of quantum vacuum fluctuations. But actually, and here was kind of big discussion about this because there was first paper of paper which shows that this Casimir force can be reproduced as a van der Waals force if we consider the plates as a source of the electromagnetic field from the, so in source theory it was proved that it can be just van der Waals forces, not vacuum forces, and vacuum only vacuum corrections that it might be here. It's corrections to the electromagnetic to field propagator between the, which is kind of gives contribution at much smaller scales and so on. Later, in Bryce DeWitt claimed that if we calculate in his book about the field theory in the space-time with kind of distorted Riemannian structure of this of the Minkowski space-time. It was one of the examples when we get some effects from the existence of such plates. But in this case, plates somehow locally changed structure of the space, of the structure of the vacuum fluctuations. That means that in this case, the only vacuum effect that can come is vacuum distortion by the plates. So it's kind of intersection between the plates. In this discussion, it's kind of classical objects, much larger scales, and the interaction of the vacuum fluctuations with the classical objects. It's questionable. Should we consider some microscopic interaction with some currents inside, or so on? There are difficulties in treatment in the perturbation theory. So
I understand correctly that Casimir energy can be thought of either as a vacuum energy or as resulting from the van der Waals interactions. And
No, but you see that Casimir energy, this so idea of the Casimir energy consists of the statement that we have different vacuum structure between the plates with different energy density. And if we subtract the energy density between the plates and out of the plates, then we get Casimir energy. And it somehow it is considered as a vacuum. But one of the proof of reality of this is the Casimir force. But the problem that Casimir force can be explained just by interaction of currents in one plate and another plate, because there can be kind of fluctuations of the charges and so on. So there are they're neutral, but they still have some charge distribution. Otherwise, there would not be conductors and so on.
Sasha, is it possible to formulate it in such a way that because we have boundary conditions, so we have a discrete spectrum inside and continuous outside. So therefore, not all eigenstates are present.
Yeah. This is standard formulation. This is standard. This is original idea of Casimir, that we have different spectrum inside and outside.
Yeah.
And then he somehow calculated and find some result. But the problem that vacuum fluctuations are not the waves which somehow propagate on the infinity. It's not plane waves. If you look, for example, on the path integral formulation of field theory, then your vacuum fluctuations is loops, vacuum loops, which live on the certain scale. That means that the loops cannot somehow affect in this way on the spectrum because Casimir hypothesis was that we have some vacuum fluctuations which are plane wave which fill all the space-time, but it's actually not true. But his result was kind of approved by experiment. The idea of Schwinger that we have some interaction between, which is plane wave between the plates, which coming from the source. And actually, in fact, on the lattice, we confirm, so we have both of the effects. So vacuum restructuring and also this interaction, because when you introduce the plates on the lattice, in fact, you put some source of the field. If you put those conditions on the fields, it's kind of sources of the fields, and then you have such type of interaction. So it's.
And how of course decays one over what?
One of the are some. I don't remember exactly. I think 4. I think, yeah. I think it's 4. Yeah. So, how it works on the lattice? How to introduce? Because usually we consider this Euclidean lattice as a kind of thermodynamical system more or less uniform, and we have average on somehow on the space-time and also on the copies of this space-time and so on. That means that introducing such plates somehow by hands can be rather difficult, because it should be somehow included in the action, these plates. So how to include them? Because we have statistical sum, which we partition function, which we cannot use as just a boundary conditions. So standard boundary conditions for the Casimir plates are following. So we have magnetic field which is normal to the plates is 0, and electric fields which is they also comes to 0. So we have Dirichlet conditions for the electric fields. And from point of view of the lattice variable, so we are working with plaquette angle, plaquette phase, which is I showed in the beginning. So we have this condition for the cosine of the plaquette angle that it should be equal 1. To include in our statistical simulation, so we use Lagrange multipliers. So we modify the lattice coupling beta in that way. So that means that at some plaquettes which belongs to the plates, it the beta comes to 1, equals 1. And then we somehow obtain some action, and then we calculate some observables with some finite beta, and then make limit of the epsilon to get correct value of the beta, which makes value of the plate contribution of the plaquette comes to 0. So this is one of the examples how we introduce homogeneity on our lattice. Then we can manipulate by beta, because beta fixes two things. So it's relation between the interaction and scale of the lattice. Yeah. So this is our beta. It's lattice coupling, which is combination, and then in fact we can somehow fix in that way in our calculations. So I will consider example of the compact U1 theory, which has one interesting feature. So it has monopoles as a kind of purely result of the fluctuations of the vacuum fluctuation of gauge theory, and analyze how the plates affect on the vacuum structure of the compact U1 theory and its phase properties. So monopoles in U1 comes from the invariancy and the discrete shifts of the theory. If we add 2 pi to our plaquette angle, then our action is invariant over this discrete transformation. Then we can define the monopole as a rotation on 2 pi times to some number which belongs to Z. And the monopole current can be defined in that way when we have such phase collected on some cube with the directions alpha, beta, gamma, and this direction of the current mu is normal to all these 3 directions. So if it can be 0 here, which is related to monopole itself, so we can have some kind of monopole currents which usually in compact U1 theory form some percolating cluster, which is fills all this space-time. And one of the good sides of the lattice field theory that we can make visualization, direct visualization of the vacuum structure. So we can have snapshot and using some special algorithm to detect the monopoles and even have some see how monopoles distributed in our space-time, and define the one of the important observables. It's monopole density. Calculation of the monopole density shows that it's also sensitive to the some phase transition. So we see that it behaves like some quantity which is sensitive to phase transitions. It points to this idea to explain the confinement as a dual superconductor. Then we have monopoles in vacuum which somehow squeeze the lines of the gauge field in some tubes, and some we have somehow confinement, dual picture of the confinement. That means that it's sensitive to confinement region and deconfinement region of larger beta. And successibility shows that it's really like some kind of phase transition. So if we look on the behavior of the monopole density outside of the plates and inside plates, we see that it's the distribution of monopoles inside and outside are different. So we have more monopoles outside. So plates themselves somehow affects on the monopoles. The simplest kind of understanding that the plates restrict vacuum fluctuation, because for monopole emergence we need rather large vacuum fluctuations of the compact field to have this phase more than 2 pi. So it should be somehow more than 2 pi. But the plates, they restrict fluctuations, and it's more or less same picture when de Wittels estimated vacuum density between the plates and saying that it's affects on the vacuum fluctuations. He also used this idea that they restrict vacuum fluctuations, and then we have somehow different behavior of the vacuum fluctuations, and so lower energy density between the plates. Here we see this picture, but on the level of small scale fluctuations, because monopoles they are local objects, even more they are singular objects in the one theory. So we have on the level of the local object some kind of vacuum restructuring. So this is, you see that at different beta we have ratio of the monopole inside and outside, and all different.
You studied the effect of the gauge group to the Casimir effect.
Yes, Oman. Yeah. Yeah, so we have here we, in fact, it's interesting, but we reproduce it will be later. So we reproduce the standard calculation of the Casimir actually, in fact, on the lattice. Yeah, so we see it, and it's interesting, but it's not actually what he calculated it was non-compact electrodynamics. It is some kind of standard electrodynamics. This is compact electronics, so there is also effect of the monopoles as well. So there are several effects, but it's strange that we reproduce more or less same result, but not because of this long range plane wave, but mainly because of the fluctuations between. Here, I would say mainly because of the monopole densities and so on. So because if you see, this is distribution of the monopole density between the plates of the different beta, and at some point we see that there is a much smaller density. You can visualize. Even we play it. We have one paper which is kind of. I think that it's kind of fashion of the neural networks. We teach neural network to detect the phase between the plates, analyzing only monopole configurations, and it's predicted the phase transition very well. Actually, only analyzing this monopole, so they reflect actually the at least phase of the vacuum. You mean this one?
Yeah, the one that particularly ordered on the right hand side.
Yeah, it's kind of technical effect of projecting all this picture. I don't know. So it's also I was also interested what happens, but it's if you look from this side to this configuration, you will see the same kind of ordered picture. So it's
On the axis of that space.
yeah. We have Here it's distance between it's x. So you have on the x-axis the plane, and here this is. So it's special cubes. So there is no time direction. So if we calculate Polyakov loop expectation, it's in the empty space-time without any plates. So we have some 1.01 phase transition here, but in between the plates, we see that dependently on distance of the plates, we have phase transitions in different points, and even Polyakov loop itself grow, and it also connected, I think, with the property that we somehow average it on smaller space, because on the larger space you average Polyakov loop smaller value it gives because of the statistical somehow effects and so on. But we see this interesting effect, and then we can. Yeah.
It looks like why there is such smooth transition. So it's,
Transition becomes also smoother.
so it's actually. Are you sure that this is a phase transition?
No, this is of course this is kind of crossover in this case. Yeah, if the plates are too close, then it becomes smooth transition maybe. So we did not. It might be even some kind of like Austerlitz-Taulis transition because of the monopoles, for example, or something. But it's like kind of infinite order. We definitely have in one case we have confinement, deconfinement, but it might be connected with properties of the monopoles. In fact. But we actually, in fact, else it can be connected with this reduction of one of the this so-called размерная трансмутация, забыл как по-английски. Yeah? Dimensional transmutation, yeah. So it might connect to dimensional transmutation as well, because we restrict one of the dimensional up to just one or two steps of the lattice, and then it becomes softer if we make it larger. So it also can be effect of the dimension of the. So we have, in principle, we have almost two-dimensional manifold here if they too close. So it's also affects. Anyway, there are definitely finite size effects as well. So I would say that because in fact, Casimir claimed only finite size effect, that we have shorter distance, it restricts some kind of spectrum of the fluctuations, then we have, but there can be finite size effects and also effects of the plates itself, which we'll consider a little bit later. Huh? This one, I forgot to mention it. You see this 20, I think that it's 24. So it's infinite temperature, so it's 4-dimensional, yeah, so it's 24, yeah. I'm sorry, I did not put parameters of the lattice because did not want to go in details into the lattice simulations, but might be it's important question, yes.
You mentioned ATT transition, so is it something usual in this system? Or?
No, I would not. I'm just my guess. So might be because it becomes soft. So it's, but we actually we did not study what kind of in details what happens. We see that there is some rearrangement of the monopoles. Actually, we detected it mainly by using this neural network application when we studied in details the monopole configurations. And in
touch the whole lattice or it's local?
It's touch the space between the plates, because the phase transition first happens between the plates. No, actually, the phase in compact electrodynamics, there is a kind of real transition, confinement, deconfinement. It's phase transition. So first order phase transition and so on. But in between the plates, it's not. It becomes different. It becomes much softer. So we can, in this sense, we can say that we can plot the Casimir vacuum kind of phase diagram. So we have phase transition.
What was the data given to the neural network?
Huh?
What was the data given to the neural network?
Excuse me.
The data.
Data for the neural network, data is position of the monopoles. So distribution of monopoles. So we somehow gave the lattice configuration in the form of distribution of monopoles.
And it was a convolutional network.
Yes, it was convolutional neural network.
So presumably it would be nice to look at the filters and see exactly what features were picked up by the neural network, because those would be the local patterns in the monopoles, in the monopole distribution, that on the basis of which it is predicting.
No, but actually it so I do not discuss it here in details, but of course I don't discuss all this neural network stuff here. Otherwise, but if I remember correctly, So it was some kind of just classification problem, and for the neural network, it's confinement, deconfinement, but also the interesting thing that the phase transition itself, it was you can determine by the error of the neural network. When you have large error, then okay, you are at phase transition. But also analyzing particular kind of configurations of monopoles, you can see that in one case it's kind of percolating cluster of this monopole currents and so on. In other case, it becomes pairs of monopole, anti-monopole, which are kind of rare in distribution, but it's not separated. It becomes kind of pairs of monopole, anti-monopoles, and then you have deconfinement in this case. Yeah.
Thanks.
So this kind of phase diagram, so this beta critical somehow change dependently on the distance and on the beta. So we can see this is phase transition in empty space, and at a rather large distance between plates, we kind of reproduce properties of it. And another interesting thing, which we also will see in some our other examples of non-uniform systems, that we have in our lattice, we have different regions with different phases. So we have confinement here, deconfinement in between. That means that it's somehow smaller effects of the smaller distance works like a kind of finite temperature effect, actually. In fact, so it shifts beta critical. That means that it's somehow effect of the temperature in between the in between the plates. So it's a rather interesting effect. So let's have a look on the SO3 theory and the corresponding. Here we analyze Casimir energy. So this is the definition. So it's plate conditions. So we just have to include color here, but the color itself does not play a big role at this moment, but will play later. So this is energy momentum tensor density. Then we can define energy density for the zero component. And in the Euclidian case, we have this formulation. And then we can calculate this lattice analog of the energy density. This is particular Casimir energy density, as we already discussed here. So we have average somehow plaquettes which form as the magnetic field and electric field. And also this S means that it is a difference between the average over all lattice without any plates and between the lattice. In this way, we somehow make regularization, so we subtract this infinite contribution of the vacuum energy. So we regularize it and get purely difference of energy density between the plates in empty space. As a result, we have this kind of interesting result. So this is. You see, in lattice, it's important, you can be sure that your result is not some kind of lattice artifact if you have good scale with beta and keeping the same kind of physics line. So we see here very nice scale. Then we have fit of the Casimir energy. This is a Bessel function of the second kind. One can also fit it by some kind of exponent to explain this mass scale, but it's nice. And then here we have some mass scale. That means that this energy density between the plates has some mass scale. So we could expect that it's kind of some interaction. For example, if interaction between plates has this field has some mass scale itself, then we will see mass scale here. That means that it's exchanged some massive particles or so. Of course, in the pure electromagnetic case, it's zero. But in case of the SO3 theory, we have some mass scale which we obtain from this best fit, and it is half of JV, and it's amazingly much smaller than lowest mass scale in SO3. That means it's kind of some new particle in the spectrum in this case in SO3. So this is the mass of the glue ball, but it's much smaller than mass of glue ball. It's also purely kind of properties of the gauge group that we obtained some. But so our hypothesis first was that this new mass scale is somehow related to the excitations around the plates. This was first kind of guess that we have the main change of the vacuum in this homogeneous space-time around the plates. So it's somehow some surface excitation of the plates, and it's very similar to so-called excitons in the condensed matter when we have somehow electron which interacts with its image in the kind of mirror which is on the surface of the conductor, something like that. So it's some analogy. So this is new kind of mass scale. In fact, it was also obtained in SU2 by Karabari Nair in the thermal field theory, but they call it this mass scale as screening, electromagnetic screening mass. But it appears only in Casimir system. That is.
I think if you, as you suggest, this is surface effect, so then it should be independent on the fact that if you will take not the straight plates, but you make curves.
Yeah, it is good idea. We are trying to do it, but making curved plates in lattice, it's very difficult. No, because we tried to do it with curved plates, but then the problem that this curved plate will be not smooth, and you have some singularities on the since you're on the lattice, so you will have some. This task is not solved yet, so we are trying. We tried to do some interesting structures like kind of sphere. Even if you make sphere on the lattice, you have interesting problem how to define radius of this sphere. There are different ways. So you can define it as when you move by the links, you can calculate distance if you move out diagonal. And also there are three options I think we studied. And sometimes it looks like kind of the interesting figures. They are not even remind but always there is a. So we are trying. So one of our attempts is try to use this Fibonacci sphere, for example. So you can use Fibonacci covering of the sphere by points and so on. Then you can have triangle lattice on the sphere, and we even did one paper on the Ising model on the sphere, this Fibonacci sphere with Delaunay algorithm which defines links and so on, and find rather interesting that critical behavior of such sphere differs from the usual triangle plate. So it's and it gives critical temperature, critical value of the critical I think when you have phase transition in the Ising model, which is some kind of rational number. But there's, if you get some rational numbers, there should be reason why it's rational. Why it's not just some kind of number. So it's still open question how to make this, how to discretize all this smooth. Yeah, it's one of the not solved problem.
How compare this to plates?
No, it's a good question. Usually Casimir effect in QCD discussed only in view of some back models or something like that. So it's kind of discussing confinement back models, but I don't know. It's at the moment it's just kind of thing which is not clear how to discuss on experiments. It's not clear. So might be some analogs in the condensed matter if you can get some kind of non-abelian group symmetry in some condensed matter models. Might be, I don't know. There is another example of the surface states, this so-called quarketon, which is similar as a kind of electron, and we calculated. We do not introduce quarks in to calculate it, but just calculated free energy of the probe charge near the plate, and find that it behaves like kernel potential. So in close to the plate, it's like Coulomb interaction. When you go far, then you have linear potential. This is at some finite temperature with string tension, which is different from string tension in the at the same temperature and the empty space, but there's still can explain some kind of differences. So it's still subject for more detailed study. And in my opinion, it can shed some light on the confinement itself, because it's interesting that we obtain actually at the same conditions, at the same, because we need to study monopole distributions around if we believe in the dual superconductor picture. But in SO3 and SU2, to catch monopoles, it's much more tricky task. So you need to have some kind of abelian projection and so on. So it's and another interesting experiment is all these Polyakov loops as a probe charges. We do near this Casimir plate, two charges, charge and anti-charge, and see that if you very close to Casimir plate, then the correlator is not zero. So that means that they interact more with the images than between. And then somehow here we have some interesting excitation, which is since they are has neutron non-color, they are colorless, so they can be kind of appear as a. Here there are some kind of physical analogy coming in the mind. For example, if you take this meson coupling back model, which Tony Thomas very much like, so it looks like kind of meson-like excitations near the surface of this back. If back and back model has properties as like kind of also some Casimir cavity or something like that. Many speculations. So I still have some time to discuss non-inertial frames on the Lattice.
And some theoretical curve we're keeping against, right? Red curve. Slide before.
Where?
One more slide. This curve. What is this curve?
It's speed.
Yes.
This formula, it's kind of, yeah, it's a standard field of the correlator between the two charges. So it's kind of interaction. Yeah. It's like, okay, we could use here exponential fit with usual Yukawa potential. It's like different version of the Yukawa potential. In fact, is so it's you can say that it's theoretical because you expect something like that. It made only to extract corresponding mass scale. So in our first paper, it's our kind of next paper, on one of PRD. In our first PRL, when we claimed this non-abelian Casimir, we just used exponential behavior here as usual. So it's first mass scale. Okay, non-inertial frames on the lattice. They are rather interesting in many applications. It's discussing all this Hawking effect on the black holes and so on, but also from another interesting thing that when we have nuclear collisions, then we have some rotating state. And rotation is also kind of a frame with constant acceleration. Here we use this idea of the Tolman that if we have some non-trivial metric, then our we will have temperature dependence, non-homogeneous tempers at equilibrium. It comes from the equivalence between energy and mass, in fact. So energy, so we have some energy density related to some thermal fluctuations. Then in the accelerating frame or in gravitation, it will somehow distribute non-uniformly, and it's somehow. That means that if you take, for example, near Earth, we have or some gravitational source, so we'll have larger temperature closer and smaller temperature on the higher distances. There will be some temperature gradient on the. So it's expressed by this, where zeta is some killing vector for the system and metric, so somehow express our gravitational effect or accelerating effect. So we used here Rindler space with the constant acceleration. And for killing vector for so some thermodynamical environment at equilibrium, it's reverse temperature, which can be here defined in this way, where u is velocity of the media. So if you let's look on the some hydrodynamics or some quark-gluon plasma, so define such time. Then there's a Killing equation, which for locally static environment, the system at equilibrium, which we need for our lattice calculation. So we cannot discuss in any way non-static systems on the lattice, but we can discuss static, but in homogeneous, and then we get the following expression for the temperature dependence. If you have acceleration in the z direction, then the temperature will have this kind of different with A in the Z direction. It depends on the Z direction in that way. So it's a solution of this equation.
So in your definition of temperature-dependent case, so
Yeah.
this one, if I understand, so if you take, for instance, standard Euclidean manifold, so then
will be constant. Yeah.
But if you have, say, constant
It's interesting question. If I understand that it requires positive curvature, not negative. It's at least the derivation which I saw. I forgot the paper of this. It states that its limitation of this. So it has to have positive curvature. Otherwise, you have some kind of here, some imaginary quantities here or something. It also depends on the sign of the. I don't know. I did not do it. I mean, this negative curvature, I did not do it myself. This one I did, but it's an interesting question. What happens in case of? So we should not believe the statements in some papers. It's better to check. I don't remember some argumentation about this.
parasitic and hyperbolic manifolds.
So we have this homogeneity temperature, and then to put on the lattice, we need just to somehow to define our lattice non-homogeneous lattice parameters. So this is action. This introduced not ourselves but Karsh a long time ago with. The good side of this section that we separate scales on the time direction and in this spatial direction. So we have different because we need somehow to manipulate the time direction scales, and then this is definition of the dependence of the beta on the z direction with lattice anisotropy, and this is lattice anisotropy. It's ratio of the spatial scale and time scale, and which is equal to the ratio of the temperature on the accelerating medium and on the static medium, non-accelerating. So physics lens in the temporal direction. This one, which is we discussed in the beginning, what the meaning of this imaginary time and how it's related to the temperature. So and this defines the local temperature since A depends on Z. Then we have this definition of the temperature on the lattice, and then we use our this Tolman-Ehrenfest solution and this lattice asymmetry, and finally some parameters of the calculation. So we switch on and switch off this acceleration at some z. So here's the symmetry. So for this task we need rather large lattice in z direction. Actually, we simulated lattice with 124 in the z direction and the usual 48 or something in x, y direction. It was rather challenging numerically, but calculate, and we get rather interesting behavior of the Polyakov loop. This is kind of distance from the point where we have phase transition. So where we have in this homogeneity when the temperature, this Tolman-Ehrenfest temperature equal the critical temperature, and then we have here phase transition when we move along that direction. And we see that even very small acceleration, which much smaller than the temperature in the nuclear collisions and so on, only 5-6 MeV. It gives us a rather large effect, so it makes phase transition smooth. So it's not real phase transition. That means that it seems that in nuclear collisions we cannot see. Because of those effects, we cannot see phase transition, in fact, because of this effect. And if we actually look on the it's behavior of free energy. There is a jump. Okay, it's important now. So we have you see this ratio of the critical temperature to critical temperature accelerated and critical temperature non-accelerated. And accelerated critical temperature is rather narrow, and so it's really phase transition here. And this point is different accelerated. Even here, it's rather wide distribution of the temperature of phase transition. That means that there is smooth crossover, which cannot be detected on nuclear. Might be this is the reason why they cannot detect it. Of course, you can say that they're rotating, and here rather interesting part, how we can derive Tolman-Ehrenfest behavior from the lattice. So we can somehow do not introduce any kind of such dependence, but just introduce. Okay, then I will. So it's a standard formulation, but for the rotational, so this is dependence. For the Tolman-Ehrenfest solution for the rotating frame, this is omega, it's a kind of rotating velocity. Rho is distance from the center of rotation. And I would like to take your attention for the Euclidean space-time with imaginary rotation. In this case, we have periodically boundary conditions, which can be for the rotation along z-axis in this way. Then this is how we should close our Polyakov loop when we are calculating and our twisted boundary conditions. And we see that in this case, when we have rotation, our point here is the kind of shifts. It's not at the same. It shifts on some angle, and it's interesting. So when we move from tau 0 along this imaginary time to tau equal beta, which is another edge of the lattice, plasma rotates on some angle, which depends on the angles, and we then that means that our boundary conditions they induce rotations. Because we have periodic boundary conditions. If we have rotations, which depends, so with time, the system from one edge to another, they rotate one to another. So that means that the value of field which we can make periodic boundary condition will be shifted. And then we have boundary condition, which is gives us this type of phi here is the angle of rotation. So it rotates with tau when we go along these boundary conditions. And if we compare with metric, which comes from Tolman, they will correspond each other. But we have to take into account periodical effects, which is not the case here. But here we have periodical effects. Then, if we take again Polyakov loop as the probe charge, put this probe charge in this co-rotating medium, then we see this interesting thing that. In the co-rotating media, our probe charge going over the t direction will not go just beta this distance, but goes beta with some additional distance due rotation. Then we can express our temperature using this connection and this. we can express our temperature, and we get exactly solution of the Tolman-Ehrenfest. We did not introduce anything here. We just took periodic boundary conditions, and then we get this result for the Euclidean space-time for imaginary rotation. Because we have imaginary time, so we have here some rotation on imaginary angle, and it's transferring from imaginary angle to real angle, we get Tolman-Ehrenfest solution. So it can be derived in this sense here. And it's another interesting thing if you look on the temperature distribution, but temperature distribution reversed, because you see here we have minus, here we have plus. That means that when we have mixed phase, because we have different acceleration in the center and in outer region, then here we have confinement in the center and deconfinement in the out. But in imaginary rotation, we have deconfinement here and confinement inside. Of course, it makes some questions. Is it reliable, or can it be somehow proved that this imaginary rotation directly corresponds to real rotation? There's some questions to discuss, and also it's same as kind of introducing acceleration on the lattice itself, using all these thermodynamical tricks that when we have a kind of connection between the acceleration and between the temperature. So this is lattice rotation. Another problem here that we have only P/2, so it's minimal angle which we can have. So we cannot rotate. Yeah, so we have minimal angle. And but this minimal angle, it's rather fast rotation. It corresponds to 300 MeV. So it's rather strong rotation. But anyway, we can, for the moment, make some calculations and estimation. And also Polyakov loop definition here is rather technically difficult. So in one case we have, in static non-rotating case, we just go along time direction. But in laboratory frame, in rotating case, we need to make 4 branches of the Polyakov loop. See that we have connection here, then going on such 4-fold Polyakov loop. Of course, it gives 0 because it's too large. And actually, larger Polyakov loop, smaller value, more statistics one needs, and so on. And it's on such huge lattice statistics difficult. But there is in co-rotating frame, we can make such loop with some kind of link here, jump here. And this Polyakov loop allows us to analyze phase properties of this is mean value. And without rotation, we have here phase transitions, obvious phase transitions. But with rotation, we have just monotonic growth of the Polyakov loop. There's no phase transition at all, so Polyakov loop. Yeah.
Maybe I missed it, but so correct me. It seems to me that the difference between Euclidean and Minkowski space is just the signature. Yes, so and then Minkowski space is, it looks like de Sitter space, no?
You see the no, there is there's deeper problem between Minkowski and Euclidean space-time. So you can transfer from Minkowski space-time to Euclidean space-time by Wick rotation of the axis. But you can rotate your time axis only in integral. So you cannot have explicit imaginary time dependence in your equations, in your observables. So it's only in integral. That means that you have integral over time. So you averaged over time your observable. And then you can look on this average in Minkowski or in Euclidean space-time. It's kind of up to you. But there is also another problem. This is why I very much kind of critical to analyzing some hadron spectrum on the lattice and so on. You can do it also only in case if you do not have some non-trivial poles or cuts in your spectrum of the particle, because there is direct connection between the space-time and momentum time. But if you have in momentum time some poles, you cannot do Wick rotation in momentum time, and the same you cannot. In this case, you cannot do this Wick rotation to keep this correspondence. So usually people do not think about such kind of things, but so this is problem, and actually this is why usually lattice was very much criticized. Actually, in fact, when I was PhD student, when I was postdoc in Dubna, it was kind of forbidden thing because of all this, namely because of Wick rotation and because you do not have, that all this Bogoliubov formulation of field theory based on the kind of analytical properties of the green functions and so on. So it's main thing. And then these Wick rotations break there. So it's tricky point, and it's changing some meaning. You see here also. So even you have reverse. So in case of the Minkowski space, you have outer side of rotation will be hotter, inside will be cooler. But in even physical effects, but in the Euclidean space rotation, you will have hotter center and cooler outer sides, which is kind of looks. I don't know, but you see that de Sitter. You mean if you compare Rinder space and de Sitter space, or what? Yeah. For Minkowski, yeah. So unfortunately, so this is distribution of the values. It's interesting that in the center you have what I told, that in the center you have hotter, and you have deconfinement in the center and confinement on outer side, which is reversed. But I think that you do not have time for proteins. But in principle, I can make another seminar on proteins and so on. Should I tell it or not? Yeah, we are short on time. I'm sorry, it's too much material in one. I can just kind of pass the general idea that we have Frenet frames for description of the polymer. Its Frenet frame corresponds to gauge transformations. Then we have anti-Niemi based on this made some kind of integrable model for the. But we decided to make the latest field theory, so we used abelian Higgs model. And finally, this is abelian Higgs model. So this where scalar field corresponds to bending and to curvature, and gauge field corresponds to rotation of the. And then we torsion of the system. You see that it's. And then finally, the inhomogeneity we can add using Oka-mass term, which corresponds to interaction of these amino acids with water, in fact. Because water breaks, in fact, breaks here gauge symmetry, otherwise they would kind of rotate more or less freely. And the water breaks, and then we can introduce different charges for interaction with water of different amino acids, and then we have homogeneous, and then finally we were able to reproduce myoglobin with precision better than 2 angstrom on the lattice as a kind of lattice configuration with. And also another interesting thing that all these kinks, which anti-interpretive kink, they have different topological structure, in fact. So there are some sphalerons, some instantons, and they really somehow correspond to some amino acid. So we are developing the subject. I think that it might be deserved kind of separate discussion. It's just some advertisement on this our activity. It's interesting, and we were able to reproduce myoglobin phase diagram, but here we did trick, which I already told to Sergey. So we did not use field theory to warm the protein to increase temperature, but use this Glauber. So we took this configuration and used Glauber algorithm to heat it, because on the lattice the problem that on the when you work with fields, not with coordinates of the amino acids, but working with such integrated fields, it's not clear up to now how to treat self-avoidance. The problem, if I don't know, might be mathematicians know, maybe there are some theorems about if you have curve described by kind of in Fourier frames, are there some invariants which control other self-intersections or not? Or maybe some, because self-intersection in this case will be some closed loops or something like that. I don't know if
non-self-intersect.
yeah, but you can control some quantum number, then it's easy. So you on Monte Carlo, because in this case, if you want to do it on Monte Carlo on the lattice, you should always convert it in the normal coordinate space, and then calculate all the distances between. So it's huh? We should discuss it. If you can propose some solution, it would be great.
Okay. We should speak
Okay.
have been many talks. So
I'm sorry, too much material in one talk, but I wanted to make it some kind of review.
I'm just wondering, there have been already questions. If there are other questions. Can somebody pass my?
You said you reproduce something. What do you reproduce?
Okay, so you see, this is curvature. This is gray one, and torsion, green one, extracted from protein database. So you take protein database file with the description of the position of the. Then there is a special algorithm how to convert these coordinates into the curvature and torsion of this curve, which is. And this is what our model gives. So we have this is points which are going, they more or less on this curve and here. But one of the criteria it's RMSD. It's kind of distance, some average distance of the what you reproduce and what you have in your model. And it's about 2 angstrom. So it's actually experiments are done with this precision.
Yeah.
So they say that RMSD of the experiment, so error in RMSD is about 1 to 2 angstrom. So it's
just very quick precision regarding this. When you mentioned the sphalerons and instantons, so you define those as certain topological states that.
Well, we just analyzed behavior of the gauge field and scalar field on the lattice. There are kind of some.
But this follows from like geometrical states of this.
Yes.
Geometry of the proteins.
Yes. It comes from the geometry of proteins. А, да, можно.
Да, we cannot still zoom.
Я наоборот думал, что я в час уложусь, а тут что-то. Я извиняюсь, конечно. Ну, а сейчас, Сереж, ты предлагаешь фи-4 использовать теорию.
P4, компонент P4.
Погоди, но с калибровочным полем?
Это люди делают с колян.
Ага, видишь, нам так